Paul Taubman here with 9.Connects. I'm glad that you could join us here today. You are in the right place if you are here for the 10 things that may surprise you about designers in the PCB process. Yes, we will talk about engineers, but the reason why I made this last-minute change over here is due to the fact that there's actually a change that is going on in our industry. And for the time being, I'm going to use the word designers, but I'm going to distinguish what a designer is as we go about this discussion here today. So first and foremost, let's just talk about processes in general. We need processes because they affect our ability to design. And a balance, it's really a balance between red tape and the Wild West. And I've been in places where it's so bureaucratic you can get nothing done, and I've been in places where it's the Wild West and it is so crazy out there that you spend just as much time trying to jockey for position, to do what they call CYA emails, and to make sure that you got everything covered so that you can get your things done. And what you're really looking for in a process is something that can keep the process moving forward, but in a way so that we're not adding in any variables that could cause problems, but at the same time doesn't slow it down or create bottlenecks. And of course, no process is really effective unless we bring our skills into it. So for example, if I was reading the process on how to maintain an aircraft, it would be pretty much useless to me because I have no skill set in anything that has to do with an aircraft. I would have to learn that skill set in order to use that particular process. But more importantly here, not just the process itself, we've got to realize that there's relationships that go on in any given process. Okay? We have to communicate with each other. That's the nature of the human beast. And interestingly enough, I remember a friend of mine who's going through an MBA program, and he summarized it by saying the biggest problem with business is the humans that are in it. And it's because we all have our different quirks, our own different ways of looking at the world, our own idiosyncrasies. But the fact of the matter is we are human. We do have to communicate with each other to make these processes work. And as a matter of fact, all right, it's our personalities that really kind of make up the company culture. And I've always called it the fabric. I guess you can see here I put together a quilt. But this is how I always envision a company when I go into it, and I've been around it for a while. You get the feel for its company culture. So how does the company culture come about? It really comes about by everybody's personalities that are drawn into it. Okay? Some people have very strong personalities, and they will have a bigger piece of the fabric. Some people, by the mere positions of their jobs, will also have a bigger piece to it. But we all contribute to the fabric of the company. Okay? And as a matter of fact, just to give you a very specific example, many years ago I used to be in this organization called Toastmasters. And if you ever want to learn how to do public speaking, phenomenal organization. All right? They usually have a lot of these clubs around the area, and you can join one. Their structure for these meetings are the same. Really can't vary off these structures. They want you to do the same thing. But I've visited various clubs, and what was interesting to me is that even though they were supposed to follow the exact same process, the exact same structure, no two clubs are the same. So what was the differentiator? Well, it was the personalities, right? It depended on who these people were, why they were there, and the personalities they brought with it. So we just got to keep that concept in mind when we're dealing with processes. And as we move forward in this presentation here today. Now let's take a moment more about the human element. It has to do with this concept called perspective taking. Perspective taking for all of us is not just what we want, but how we see it. Okay, and more importantly, how others see it as well. So there's a really great little quote. Two men looked out of prison bars. One saw mud, the other saw stars. So what's interesting about this is that two men were in the same predicament. They were both in a prison cell looking out the same window. The difference was that one was looking down the mud, wallowing in whatever sorrows he may have had, while the other one was looking at the stars looking for hope. But they had the same situation. They were just taking a very different perspective. So how does one approach a design? Well, it all depends on their angle of approach. And just to give you an example over here, okay, let's go here. This is a famous commercial. It came out in the 1970s. The first time I ever saw it was in EDN magazine back in the early 1990s. I liked it so much I actually put it on my wall when I was a co-op, because what it did is it showed everybody's perspective about what they thought the swing should work, or how the swing should work, or what the swing should be. And the funny part about it is when you look at the end is what the customer wanted. So everybody had a different vision or angle of approach on how they wanted this design to work, and yet they didn't really listen to the customer. right? And that's what we see in the PCB design, in the sense that everybody has their own perspective at it. Marketing has a perspective at it. Mechanical folks have a perspective at it. The fabricator has a perspective at it. The test folks have a perspective at it. The designers have a perspective at it. So all of these personalities are coming in with their own perspectives of how the process is supposed to work. And as a result of that, you may have found yourself in situations where you look at the entire PCB process and you say, look, we've got some really brilliant people working on these design teams, and yet we can't seem to get our act together. These processes seem that they take far longer than they should. We're doing far more respins than we think we ought to be doing. It's becoming more expensive to do these projects than we expected them to be. Schedules are not being met, and it goes on and on. So a lot of times, not just the process itself, though the process should be reviewed. A lot of times it's just understanding what I'll call the human element that is a part of that process as well. So, and that's really the point I was just making here with this last one. The PCB design flow is just really no different than anything else that we see out there. Any process has a human element involved in it. So let's get to our top 10 list. I think first and foremost, it's really important for us to understand the difference between engineers and technicians, because this line has been absolutely blurred in the last, I'd say, 15 to 20 years. Okay? And we need to understand this because when we look at the PCB design process, those people who have a lot of experience in this process are generally not engineers. They're actually technicians. Most of them started off as technicians. They had to do layout work. They became very proficient at it. They came around the time the CAD programs are out there. They sat down, they learned these things, and then as it just kind of systematically progressed, they became really true experts in PCB design. Okay? These days, it's really the engineers who are now doing the PCB layout. Okay, so what transpired? What's going on? Why do we switch from technicians over to engineers? Well, let's first and foremost understand what the difference is between the engineer and the technician. The engineer's role has always been theoretical, and academia still operates this way, by the way. Okay? It's always been on the theoretical side of things. So they design things, calculate, analyze, simulate, and test. And in fact, when you think about the design side of it, we're talking about schematic capture. Well, what's the interesting thing about schematic capture? Well, schematic capture is, number one, it's dimensionless, right? In fact, if you're familiar with Altium Designer, what do they call it? They call it DXP units. They do that on purpose because they don't want you to think that you're working in mils or that you're working in millimeters. So they created this this system called DXP units just so that we could keep to the concept of the schematic capture, that it's supposed to be dimensionless. But secondly, we work with symbols. And if you look at the picture over there on the right side, well, what type of symbols do we see? If someone's not familiar with electrical engineering, they have no idea what they're looking at. For me, I see a bunch of resistors. I see a bunch of transistors there. I see one operational amplifier. It looks like I see some power sources or actually current sources there. Right? I know how to read these things because I've been trained in that. But this is all symbolic. That's what they do. They draw things in a symbolic form. Okay? Whereas technicians, their role was the implementation side. Right? They did the layout of the boards and the cables. They did the purchasing of the components. They did the soldering. They did the lab maintenance, right? The only time the engineers ever came in the lab was to do any type of testing. And most of those design engineers never even bothered going into the lab, especially if they were in larger companies and they were considered to be design engineers. They would never touch the test equipment. They would be far removed from it, especially in the ASIC world where they were doing computer chips. I certainly saw that, and that's still going on as well. Now, the reason I bring this up is because there's kind of an interesting thing we do in the PCB process. Okay? We actually have two steps, which is, if you think about it, kind of odd, because in the mechanical world, they have one editor, and they draw things. Now, they can show things in different perspectives, but they usually have one editor. Same thing with the system folks. They can draw something in one editor. They, again, can show it in different perspectives, but it's one editor. Okay? Same thing with the civil engineering folks. So why do we electrical engineers seem to have to do with two editors? We do one for the schematic, one for the layout. Well, that's because the schematics were for the engineers, and the dividing line between the engineers and the technicians was between the schematic capture and the layout tools. In fact, that's why most of those tools were built separately to begin with, right? You had your schematic tool, and then you bought a layout tool. And the layout tool is for the technician to use to actually do the actual layout, where the schematic tools were just simply there for the electrical engineer. Right? And I find this kind of weird because now that this line has been blurred between what an engineer does and what a technician does, you'd think that now there would be a tool out here where when you're doing the schematic layout, you're almost simultaneously doing the PCB layout as well. Now, there's a lot of tools out there that will push the net lists over, and they'll obviously put the components, the footprints over to represent those, and they'll at least have lines to connect them to show the theoretical connectivity, and then we've got to place them around them. But it's almost interesting to me that it's not to the point where it's like when you place down a schematic and you're going to do its connectivity that you're not almost doing this simultaneously with the PCB at this point. But there's a reason why we have these two tools out there right now. It's kind of a part of an antiquated process of the technicians doing the layout and, again, the engineers doing the schematics. Excuse me. Now, so where did the line get blurred? Well, there's really been a lot of consolidation in our industry, and there are really three economic events that happened here in the United States that drove that. So the first one really started in the early 1990s, the post-Cold War. So prior to really the, let's say, the internet boom and the dot-coms and all the other good stuff that we know today, the biggest consumer of electronics was by far the United States military, right? Because they were in a Cold War with the Soviet Union. They were always building new military equipment. There was a lot of money being spent over there. Now, by the 1980s, digital was getting big. People were starting to buy home computers along with printers so they could do word processing and spreadsheets, and of course a bunch of games. There were video game consoles out there. There were a lot of handheld devices that were out there. There were, there were arcade games that were coming about. We were starting to become a lot more digital back in the 1980s, but still the United States military was far the biggest spender in electronics. During the 1990s, well, we had peace finally, right? The former Soviet Union basically fell, and these countries that were used to be communists were turning into democracies. The military spending was not necessary anymore, so there was a big pullback on that. But during the 1990s, we discovered that we could take our computers and through this thing called the internet, have them talk with each other, right? So the internet became this really overnight sensation. Now, the internet had been around since really the late 1960s, early 1970s, and oddly enough, its purpose was to communicate information with each other. They didn't even build it to have it password protected all that much, or if you did, it was just to kind of keep those people who shouldn't bother with it off of it. But the idea was that once you were on it, you shared information, which is interesting because these days, I think we got on it and we got to have all our passwords to get anywhere with it. But it was really supposed to be just an open source of information. And it had always been there. It's just that back in the mid-1990s, people realized that, hey, if we create a nice interface for this and we put up these sites and make them easy enough to create, then companies would put these up, individuals could put them up, they could actually do these things called e-commerce, and all of a sudden we had the birth of our internet. And what was amazing about that was that really by the time we get to the next step here, the tech wreck of 2001, well, guess what? We overbuilt it. It only took us 7 years to build a massive infrastructure. I remember reading one thing about Owens Corning, which had done almost all the fiber optic. They were the ones who were leading the sales for fiber optics being put in the United States for this whole new internet. They said by the time everything was said and done that really I think only 6% of the fiber optic was lit, right, by the time this tech wreck came about. So there was all this bandwidth that was put into the ground, all this infrastructure put in the ground, and we just simply overbuilt it. I don't know if you remember this as well. I certainly remember it, and it was kind of a neat thing. There was this thing called the Y2K bug, and a tremendous amount of money was spent on everybody basically trashing old systems. And in one sense, it was nice because older systems were very proprietary and they were difficult to work with, and so it just gave everybody a really good excuse to get rid of old equipment and buy new equipment. So unfortunately, by 2001, we had our tech wreck. A lot of companies consolidated. You know, Hewlett-Packard is not the company today as it was before. Sun Microsystems, which had been around forever, eventually just faded into being purchased by Oracle. Just a lot of companies really suffered back in that 2000 run tech wreck because it just got overbuilt. A lot of engineers lost their jobs. And then, of course, in 2008, we had the Great Recession, and people call it the housing bubble, but the fact of the matter is it impacted everything out there. And as a AP teacher had told me once, he asked the class a question, what's the difference between a recession and a depression? Well, he jokingly said, the recession is for the guy who still has his job. The depression is for the guy who doesn't have their job. So it was, a lot of people call it the Great Recession, but quite frankly, a tremendous number of people, including engineers, lost their jobs during that period of time, and it was very difficult for it. But as a result of that, engineers were just happy to keep their jobs, right? Admins and technicians were constantly being let go of, and there was a very general assumption in all three of these instances as these contractions were happening that engineers were smart enough to handle it all. And I love this little picture I found here on the internet because I think this is how we tend to think of engineers, that these individuals can multitask and do all these really great things just like a secretary, but at the same time be an engineer. Well, engineers are not writers, and I'm going to talk about this here in a few minutes. Most engineers are not secretarially oriented. And what I mean by secretarially oriented is I'm talking about the fact that to be secretary oriented means you can take phone calls, you're taking down messages, you're checking your emails, you're scheduling and appointing, doing things that when you need to for whoever needs to be done, that you're extremely organized. All right, and that's not normally what I see with most engineers. And most engineers are what they call creators, not administrators anyway. If they wanted to be administrators, they would have gone into a different degree. Engineers, most engineers out there that I've ever met, including myself, why did we get into this? Because we wanted to create things, to either make money or to make the world a better place or both, right? We didn't go into engineering to become basically paper pushers. So this is a great example of, and I haven't seen it to this extreme, but I've seen a lot of deaths of what I'll call brilliant engineers. And Bob Pease, who is legendary with National Semiconductor, which got bought out by Texas Instruments recently over here. But the thing is that Bob Pease was known for these notoriously messy desks. Okay, so was Bob Pease a phenomenal engineer? Yes, he was. Was he a great secretary? No, he wasn't. So the idea of these engineers becoming these all-purpose administrators and technicians is really a farce. It's just that's not the way engineers are, the way they think. Okay. Just as a side note here, if you did see the equipment, notice that this equipment is test equipment, right? So he was an engineer, he used test equipment. So I just want to kind of bring back to the point of what was the purpose of the engineer. The engineer wasn't there to solder or to lay out boards. The engineer was there at the time to actually do the design work and to test it. Okay. So the second point I want to bring up is that a senior design engineer is not equal to 3 junior engineers. That may look true for the accounting paperwork, but in the engineering process, that's not true at all. So for example, who would you trust? Would you trust a new doctor or a doctor with 20 years experience? Let's say you found out that you had cancer. Are you going to go to the new guy who just got his medical degree and say, well, I'm going to give you a shot. You look like a smart young man or a smart young lady. I got cancer, give me a shot, or give it a shot. Let's see if we can prove your worth. No, we're going to go to the doctor and say, hey, look, you've been at this for 20 years. All right, what I got over here, how do we need to cure it? What are your stats here? Okay. Same thing with the water heater. If the water heater explodes, you're going to get a handyman who's going to run down to Home Depot, quickly buy something, put it together. May or may not have done this before, maybe seen someone else do it. We're going to deal with the master plumber who's going to buy the right equipment, put it in right. It's going to work. Or in pro sports, if your favorite team, they all of a sudden decided, we've got a phenomenal quarterback. We think he's too expensive. We're gonna trade him off. We're gonna bring in this rookie that he looked good in college. We've never seen him. It'll be his first year. Let's see how well he works. How do you feel about that, right? You're not going to be very happy because you want the experienced quarterback. Well, so therefore, in all these cases over here, we're talking about skills. Everybody really had the skill set. The big thing that we were looking for is the experience. And that's the same thing that comes down to when we're dealing with design and PCB as well. So for a senior engineer, they've grown up with the industry. They literally have grown up with the industry because this industry is really new. It's not a industry that's been around for a couple hundred years. It's only been around for a couple of decades. So they've seen this industry and they've seen how it's changed, and they've adjusted to those changes. They've also made all the mistakes. Okay, and they've learned from those mistakes. And what's interesting about that is that if you think of a respin, and I don't want to look at it from a negative perspective, but respins are things that you can learn from, but you pay from those learning experiences, right? If you get rid of a senior design engineer and you bring in 3 junior design engineers, well, now you're going to pay for 3x the mistakes because there are things that you just learn through experience that you may not necessarily pass along. And they're going to have to learn those, and they're going to learn it times 3. Okay. And, of course, they know the process. They've been through the process, right? And a fresh grad's not going to know the process just coming out of school. All too often, and I'll go to this next point here, you'll see this, we think that just by getting an engineering degree, you know everything and that you can be thrown at anything. And that's really just not the case. So let's get on to, actually, before we do, there's a couple other things I wanted to talk about. our industry in general is getting into what I'll call a difficult spot. There was an interesting thing that I attended a couple of weeks ago from Mentor Graphics. They were talking about their pads tool. Just want to see what they were doing with it on their end. But prior to them doing all the features that they were doing with their tool, their marketing manager came out and gave some really interesting statistics about the industry in general. And what they said was that, and I'm consolidating this here because they did a bigger breakdown of it, but as of 2016, only 27% of the PCB designers are under the age of 45. That's a huge statement. What that's telling us is that 73% of the designers out there are over the age of 45, all right? That a lot of them are getting ready to retire because actually most of them were in their 60s. And we're not really replacing their information or passing along this information from them to the next generation. Now, granted, these are individuals who've had really thick skin at this point because they've survived 3 of these economic downturns, right? So they're the survivors of it. So they're not really willing to give away the secret sauce that allows them to stay active at their companies. So that's an issue that we have to deal with. But the second issue is this, that PCB designs are really becoming very complex. All too often I hear this, it's almost a snide comment to me that PCB boards are so low tech. Yes, I guess once upon a time just drawing a line from point A to point B was not that difficult. However, with high-speed design, drawing a point A to point B is only half the story. That's assuming you can get through all the dense routing. But if you don't have the board set up correctly, and we've spent numerous hours talking about this in our various webinars on how to do this, but the fact of the matter is if you don't set this up correctly to begin with, yes, you may have a connection from point A to point B, but by the time it gets to point B, your signal has absolutely no integrity to it. Point B doesn't even know that you sent a signal because it's all noise, right? So this type of information, this PCB complexity due to high speed and RF, that is one of the things that they do teach new engineers, not just not in terms of PCB, but electromagnetic theory, right? And that's what's going on over here. So at least the engineers coming out understand that concept. And in the end, you'll have to pay top dollar for experts if we don't remedy this issue here pretty soon. And I'll give the example of the horse and buggy. So about 100 years ago in this country, there was a whole economy built around the horse and buggy, right? Pretty much everybody who needed a horse had a horse. There was horse breeding farms out there. There were alfalfa farms out there growing alfalfa for these horses. There were places that made buggies. There were places that made buggy whips and harnesses and saddles and everything that you ever needed for a horse. All of a sudden, this automobile comes around, and people see the benefit of having an automobile. And pretty soon, this entire industry really just goes into a full-on collapse, right? The horse breeding farms systematically start closing down. There's not as many fields dedicated to alfalfa anymore. All these places that were making all this equipment for horses, they all basically closed up shop. And I bet at one point it was really cheap to buy this stuff because nobody wanted it, and there's far more supply than there was demand. Well, now, especially if you have a daughter who says, I want to ride horses, and you ever looked into this, it's extremely expensive. Why is that? Well, because there are survivors of that industry, right? There are certain farms that were able to survive because they said, you know what, even though the general public doesn't want these horses anymore, I can still breed them for specific purposes, maybe for racing or for leisure or for a certain type of clientele that wants these particular horses. And same thing with the alfalfa, the same thing with the, those people who made this equipment here. So if you ever get involved with this type of thing, you're going to find out that it's all expensive, right? Because really the supply is very low, but the demand is higher than the supply. And I bring that up because that could happen with us here if we're not smart about transferring this knowledge of these PCB designers to the next generation. All right, so that's why I bring this up here. So think twice before just getting rid of that senior designer who's just driving you crazy, because just replacing this individual with 3 junior engineers or designers is not going to solve the problem by any stretch of the imagination. And if anything, it's going to cost you more in the long run because they are going to make mistakes in learning it. So the unreal expectations is that engineers leave college knowing hardware design, and that's just simply not the case. And the second one is that anybody can just jump in. Now again, 30, 40 years ago, technicians in particular, they may have gone to a tech school, but they would also hire these individuals out of high school if they showed savvy. And the idea was that you just connected from point A to point B as long as you follow a set of certain rules. That just doesn't happen anymore, not with high-speed design. You've got to have engineering principles, especially in electricity, in order to do high-speed design. Number 3, now I'm actually going to talk about engineers, okay, because this is the new generation that's going to be taking over PCB layout here as this industry moves along. Number 1, if engineers are that cookie cutter, then the posting for the jobs would be just be much easier process than the craziness we go through right now, okay? We would be filling out forms, not resumes. We'd be treating it basically like a stock boy position. You go to a retail store, yeah, you know, I want to be a stock person. Well, here's the form. You fill it out. You don't bring a resume for that. But if our job was that cookie cutter, and our academic training was that complete, we'd be filling out a form, and really it would look like this, right? We'd go to the want ads and we'd say, oh, electrical engineer. No further description necessary. It's just a matter of which company you want to work for. That's how it would look if electrical engineering was that encompassing a degree, but it's really not. What I want to do is talk about, let's say, 3 students. This is kind of based on an example of myself and 2 others that I worked with quite closely when I was a student. We graduated from the same school on the same day with the same degree. We took the same courses together. Okay, we studied together, and yet we all came away with different skill sets. Okay. So that doesn't make sense. If we did all these things together, shouldn't we all be cookie cutter, right? Well, you have to understand the initial conditions as well. We all came from very different high school experiences. For example, in my high school, we had no engineering whatsoever. Where one of my friends, her father was actually working at Los Alamos, so engineering was a very big part of her life. And the third friend, his older brother and his father were both engineers. So we came from very different experiences from different parts of the country. We had different hobbies and interests. We very much saw the world differently. Okay, some of us were more engineering oriented, some of us were more management oriented, and some of us were more, I'd say, money oriented. We were more interested in chasing maybe more of the money than necessarily chasing the engineering. Each had a goal in life that was very different. Okay? We excelled in different classes. For example, I wasn't all that great in analog, but when it came to hardware architecture, I had done so much of it in my co-op, I was actually TAing a number of my fellow students in it, right? So I went from, okay, help me, to, okay, I'll help you. Different co-ops and internships, what we did with those companies and those positions that we held were very different, and we were eventually hired into different companies. As a result, if we had a reunion today, you'd see that we had very different positions in the field of electronics, and we work at very different companies. And even our career paths were very, very different as well. And it's funny to me because we go through this whole process of hiring in engineers, and we put out these huge descriptions of what we expect the engineer to do, and we go through this big interview process to make sure that people fit the bill. And then the weird part is that once we bring them in, we think that we can stack engineers like Lego bricks. Well, we've got this one guy working here, then we can just throw another 3 on here and we'll triple our production or our throughput. And that's not the case because, again, what we saw initially when we hired them in is that they are actually very different people, and we hired them in for very specific tasks. And so we've got to get out of this mindset that we can just an engineer. No, each engineer came in with a skill set that we need to use in order to make this process work rather nicely. Engineers are just not taught specification writing. Okay? If I thought there was ever a benefit to any type of undergraduate engineering program, there is no foreign language requirement, and there are very few term papers that you have to write. As I'll just relay this one story you might get a kick out of. My very first day of class when I was a freshman actually started with a calculus class, and it was the TA session just because it started on a Tuesday, not a Monday. So it wasn't a lecture, it was the TA session. And the TA came in, and he had a piece of paper in his hand, and he handed it to the first person there, and the very first words out of his mouth was, "Please pass the shit." And I knew right then that I may not have a foreign language requirement, but I'm going to have to figure out I'm going to have to figure out everybody else's English. So that was the, even though there wasn't a foreign language requirement I had to study for, there was still a foreign language requirement of me communicating with the TAs and even some of our professors as well. There were far few term papers that we had to write. In fact, we had 3 unit credits, not 4 unit credits, and that was because there was no term paper element of our classes. What did we submit? Formulas, program code, lab reports, right? And even for a lot of people, those lab reports seemed to be agony for them because they actually had to write out conclusions. So what did we rarely submit? Term papers and essay responses, okay? I tell you just another story here. When I was doing my co-op credits, I actually had to write a term paper for some of my elective credits. So not just elective, but they were design credits. And I submitted in this term paper so I could get the credit, and it came back with a CS elective. And I said, why do I have a CS elective? I'm an electrical engineer. And they said, well, your paper was obviously in software, so we can't give you hardware credit. And I actually went to the professor being rather cordial about it, but explaining to him that no, actually what I created over here was actually a floating point converter in hardware. I did it through an FPGA at the time. And he said, oh, okay, yeah, okay, I see that. Yeah, we'll change the credit. But now if I was a little crass with him, I'd say, why didn't you read the damn paper? So I just thought it was kind of interesting that here I was struggling enough to put together a term paper, and yet they didn't even read it, right? They just immediately said, oh, floating point converter, software credit. So that that's kind of shows you how many term papers these guys are reading, let alone having people write. So there's some false expectations out there. What are they? Technical writing is not part of the engineering curriculum. It really is not. There were some classes in patent writing. There's a whole story behind that. I won't tell it because of our time here, but most people didn't take it anyways. It was just an elective class. And an engineer, and this is one thing I noticed, especially in the defense industry, one of the most cruel things you can do to an engineer is put them on a document for 100% of their time for 3 weeks. Because number one, engineers, again, just don't really like to write, but more importantly, nobody really can write for really more than 3 hours a day. Now, I've written a lot of manuals. I've written 2 for Altium, 1 here for 9.Connects, and I've also written a book as well. And I can tell you that in all these situations, that I can maybe write for almost 3 hours, 4 if I was just really on a good roll. But after that, the mind just doesn't really function at that point in time. So just keep that in mind, that this is quite a torture to put someone on a writing assignment when, quite frankly, they're not taught in it, and it's just not the way they think. So what are the results of this? Well, one of the biggest problems we see in the PCB design flow is that there's no specification unless it's actually demanded of the designers. What's the first thing that we do? If we have a design thing, we just go straight into the schematics and we start designing, right? Because that's the fun part. In terms of communication, we have a loose chain of emails used to communicate the project, which are not fun to go through when there's an issue and you've got to figure out what happened with where. And I've had to do those before. It's just a jumble of things because a lot of these things branch off, and then people use the same headers even though it's on a completely different topic, and it just makes it difficult to really follow the whole chain of events that happen through emails. Unfortunately, no test plan comes of this. Excuse me. No workflow comes out of this. Really, no workflow comes of it as well, not at least one that people can follow time and time again, and there's no templates. And what really happens with this is that everybody has documentation that even though they're working for the same group, same company, it just doesn't look the same. It's not uniform. And for the workflow, that's also difficult too because it becomes a potluck where someone may actually follow a very rigorous workflow and they always get it done right, and another person doesn't follow any workflow. Sometimes they get it, sometimes they don't. So it puts a lot of variables into whether or not this is going to be successful or not. Many jobs in academia are just not taught. Many jobs in engineering are not taught by academia. Here's a list of them. In fact, almost every job I can think of requires some level of what I'll call on-the-job training. And here's something that I always remembered about. This is a wafer probe setup. And if you look here where my cursor is located, this is I think an 8 or 12-inch wafer, and it's going to be slid underneath this thing, this green board here, which is called a load board. You can't see it very well, but in the very center, there's probably a bunch of really small tungsten tips. So you're going to take that plate and they're going to lift it up to those tips, and each area is going to make contact with each one of the chips on this wafer. Okay. If you don't know how to drive this properly, you will damage. Probably in about 30 seconds. Do about $10,000 to $20,000 worth of damage to the load board and the wafer in real short order. So do you expect somebody who's just straight out of college to know how to work one of these things? The answer is no. They've got to be trained on this so that you don't cause that much damage. And I've seen it done. Fortunately, I was able to avoid it. I was always sweating bullets when I was running these things because I knew what was at stake on them. But even even those who had years of experience with it, I just remember this one fellow, I won't mention his name, but he had well over 30 years experience. He just came in and he was just disgusted with himself because he actually did unfortunately slam the wafer plate into the tungsten tips and damaged both the load board and the wafers. But here's a guy who had 30 years experience, right? So look, the equipment that's out there and what we need to learn, it's just something you have to do on the job training. I know people don't like that concept. They want somebody who already knows that kind of thing, but the fact of the matter is, just especially like in PCB design, we do have to learn it, and there is a level of on-the-job training. The big thing is that engineers are not really taught administration or business. So engineering and business really do mix like oil and water. That's my observation, because what you do in engineering and what you do in business are really two different things. And if you have either side of it get amuck, then they can ruin the company. I've seen it where a bunch of engineers got together thinking that they could come up with the next greatest widget out there, and they just burned through their capital in an unbelievable rate. And then really when you looked at it, it was a cool idea, but they didn't know how to market it. And I remember this one particular one, it was a supercomputer. We were working on it. They used gallium arsenide rather than silicon. Gallium arsenide takes a tremendous amount of power. It's more difficult to work with. The yields are not as high on it. And they eventually did beat the benchmark for Intel for about 1 month before Intel rapidly came back with a new system that could replace the old benchmark set by this new company. But in the end, their system ran so hot and it took so much power that no one could obviously use this for home use. It had to be used for an institution. But the problem is that most institutions have moved on to things like the Microsoft platforms where they don't want these big dedicated systems anymore. On the other end of it too, I've also seen companies, by the way, it's like where the accountants have run amok and they look at engineers really more as headcount, and as a result the best engineers leave the company. And they may say, well, you know, we still have product, but they're not looking 3 or 4 years down the road when no new product is being developed, because those people who had that mind, you know, who really were making those contributions to the company have left because they didn't like what was going on with the management. So the other thing too is that the engineers are not required to take courses in business. Really aren't. Maybe you might be able to take them just because of a general elective that you can take an undergraduate program. But as a matter of fact, that was the original program of the original purpose of an MBA, Masters of Business Administration, were for engineers. They were actually designed for engineers, and I find it odd because everybody else seems to be taking MBA programs except for the engineers these days. Number 7, engineers tend to be global thinkers, not global thinkers. Okay, and I'm going to put up a letter, and when you take a letter, think of what the first letter is that comes to your mind. So here it goes. You ready? All right, now that you had a moment to take a look at it, if you guessed the letter A or saw the letter A, then you are what they call a local thinker. And if you saw the letter H, you are actually a global thinker. So this is one of the ways they can test for local or global thinking. Now, I'm not saying that if you're a local thinker, that's a bad thing, or a global thinker, that's a bad thing. Just most engineers tend to be local thinkers. So how does a local thinker operate? Well, there's a focus based on depth, not breadth. Okay, so they're looking at really what's in front of me here, not necessarily having to look at the whole picture. And really for the concern of the local thinker is, okay, I've got this thing coming in. What do I need to do to get this thing out the door to the next step? Okay? And what we see all too often is that companies tend to departmentalize things, and they kind of contribute to this idea of local versus global, right? They departmentalize things because it's a lot easier for them to know, or maybe to resource their pools together. For example, they'll say, well, we have a design group. Well, we have a layout group. We have an embedded group. We have a mechanical group. We have a library group, right? They break up these things into individual pieces because it's a little bit easier to do sharing of tools or resources, and then, you know, for their matrix concepts that they use. It's just, for them, it's just a lot easier to do. But the problem is that we never teach the entire process, or that feedback is never given or far too late. And the reason I show this example of what they call the grimoire chip was because that was a perfect example of what happens when thinking gets a little too local and people don't understand the entire process. So before I went into the PCB side of things, I actually started off on the ASIC side as a test engineer. And we had this one project called Grimoire, and the designers had designed it. Finally came down to the test floors. We put it on the testers. The device is not working. Okay. We try a number of different things. We keep on bugging the designers for more test vectors because these are the ones who run the simulations on it. We take their vectors, put them into the test systems. Nothing's working. We go back and forth for really a month at a time. Now, the designers have already moved on, okay, and there's no money left in the Grimoire project anyway. So the program manager's not very happy that we're harassing his designers because they've already moved on. He doesn't have the money for it. Hey, let's let's move on, guys. Figure out what's going on in your test stuff and move on. The designers claim that everything's fine. So finally, after a month, we had to bring them down to the test floor, and we had a big powwow about it, proving to them, it's like, look, these are the problems that we're having. This is why it's not working. We try to slow down the clock, speed up the clock, try to move things a little bit differently, and it's just not working here. So what was interesting to me is that during that whole conversation, one of the guys said, "That's our chip," like excited, like he'd never seen what the end product looked like before. And it dawned on me that these designers see the world from a very different angle. See, when the designers are working, they see everything. They can put a probe anywhere in their design, and they can find out what the current is or the voltage is or what's going on, because they have that visibility through their simulation to do so. On the test floor, the only visibility that we get is through the pins. We have to excite the input pins and see what comes out on the output pins. So we're extremely limited. Where they don't see it, they don't get to see it that way. So as a result of that conversation, they did go back. They found that they missed some things in their simulation, and they had to do another batch of these chips here. But what I asked our program manager to do, and he obliged, is I said, can we take these dead chips that we've got here, put them in acrylic so that our designers understand what their end product looks like? And he agreed to do it. And so I did get one of these blocks with the chip in it. But it was always a reminder to me that this local thinking of, well, I'm just going to design this thing and then I'm going to push it out the door because my part of it's done, doesn't contribute very well to the overall project of the project being successful, right? Because later on, and it was about 3 months later that we finally got these chips, and then we spent another month trying to prove that the design was not working. So that was a lot of time that got lost. And by the time we did do that feedback, well, what happened? They were already moving on to the next chip. And by the way, making kind of the same mistakes that they made on the Grimoire chip as well in terms of testability. But that's a topic altogether on another day. Engineers take the path of least resistance. And it's not really meant to be a joke. It's just the fact of the matter is that engineers really do have to find sometimes the easiest way to get things moving. And it's just not due to laziness anymore, because time's just not on their side. If you look at yourself, very few engineers have a 40-hour work week. Most of them have at least 45 or more hours. Most of them can go as many as 60. Engineers are generally not paid overtime unless you're working in defense, and the downsizing does not equal less work. And that's what I see all too often, is that an organization will downsize, but they still expect all their products to be out the door on time. It's kind of like, I always joked about this when I was working in the military, defense contracting. It's like, you want me to mow this acre of grass with a push mower within 45 minutes. Oh, and by the way, we're going to tie your hands behind your back. You have to push it with your teeth, right? That's kind of how it feels sometimes, because there's just so much thrown at you, and there's these unreal expectations that you can do it in the time that you can. So as a result of that, a lot of times you just take the path of least resistance. What can I do now so that we can just kind of keep this thing moving? Or worse, if it's a hostile environment, what can I do to keep my manager appeased, right? And then another aspect of this is a lot of times things get skipped, and these are the little things that actually cause a lot of problems in the PCB design process. So for example, this is a favorite of mine. It's called the description field of a component. This description field is really critical, because a lot of times this description field is the only thing you have in a database that describes the component. So let's take a look at what it looks like here. So here's a description here. And this description information, which we could find in the library, if there's enough information here, would eventually propagate its way into a bill of materials, which in turn would propagate into a purchasing database. Okay? And so it's really important that this gets filled out when any time a new component is being created. Right? It's critical because it's the essence of the component is described basically in one text field. It's only readable it's probably what I'll call the only readable field in a purchasing database. Any of the other fields, you probably have to look up something else in order to get it, like it's a document number, or you'd have to go on a website to find some more information about it. And it's extremely useful for sorting things here too. And yet it's never filled in correctly, because what's happening? The engineers are taking the path of least resistance. Why? Because as far as they're concerned, it's like, well, that's a great thing. If I had more time, I'd fill it in, but I got to keep on moving. And so a lot of the takeaway from this is that if we can set up things so it's easy enough for them to fill those things in, they will do it. But if you're saying, hey, I have a blank over here and I want you to follow this 20-page document that explains to you how you're supposed to fill this in, they're not going to do it. right? Because they just got to keep things moving. I'll get to it later. The later never comes, at least in terms of time available to do it. So electrical engineers are not taught process, and that's the big thing that I was trying to drive home over here. If you look at everything we've been talking about the PCB design process. We've been talking in odd sense about libraries. We've been talking in odd sense about design and layout. We've been talking in odd sense about specifications. They're just not taught these things. So what are they taught? Well, they're really taught the theory of the component and the theory of the circuit, right? What we did in our classes, we would take this transistor over here and we dissected it. We found out all the things that make this transistor work. We did the same thing with operational amplifiers. We also did this with our resistors and everything else. And then later on, we took these little pieces here and we created bigger circuits and saw how those things work together. But that's all we did, because again, academia works in the theoretical domain, right? What engineers are not taught, they're not taught manufacturing processes, they're not taught PCB layout processes, and they are certainly not taught ASIC processes. Again, these are the chip processes here. They're just taught circuit theory, okay? And then lastly, just to really drive home this point, engineers are just not trained in PCB layout. So what did they do in their labs, you may be asking? Well, for us, they were protoboards, right? Protoboards are great because you stick parts in there and you drop these wires in, you connect them from point A to point B, you mess it up, you can pull it apart and use it again. But they're only good for 5 megahertz because of the amount of noise that they create. Then, yeah, maybe if you were lucky, you could do a wire wrap board, depending on if they had the equipment for it or the need for it. This is one I actually did in college. And then there's the CNC machine. I remember a friend of mine somehow coaxed a professor to buy a CNC machine, but his whole project was going to be not only to do the printed circuit board and do it out on these 2 pages, it was going to also, probably 2 pages, 2 layers. He was going to also have to set this machine up and get it running and then show other people how to use this machine. And he had to do it in 1 semester's time. That is a lot of work, but he asked for it, so they gave it to him. In terms of PCBs, more than likely, if there was a PCB, they gave you one that was already made. And it's interesting to me, I wish there was one I had because it was for computer architecture. And then thinking about it, I know it was a 2-layer board, and that probably now explains, now with my new knowledge of printed circuit boards, probably explains why we couldn't get half the things to work, because we were probably working on speeds that board was not designed to handle. And then lastly, PCB creation. Most of these places are not necessarily going to do PCB creation because it just costs money to fabricate and assemble. So if you're kind of thinking, it's like, well, what are these guys doing in the lab? Well, yeah, they are doing circuits, but you got to understand where they're doing the circuits or how they're doing the circuits. They're certainly not really doing them on PCBs. And if they are doing them on PCBs, you really got to question how much knowledge they've been given to them or how much knowledge the individual had who made them, right? And in fact, these days, there's so many of these prefab boards out there like Raspberry Pi and the Arduino boards there, you don't even have to come up really with a PCB anymore. You just buy that off the shelf and then you program it and away you go. I mean, that's pretty much what I see in almost all the robotics going on in the high schools these days. So there's very little PCB creation going on because there's just so much product out there that you can buy that's already been prefab for your purposes. So those are our top 10 things over here. Just a reminder that you're here today because topics of this nature are important to you, that processes definitely affect our ability to design. I think we've kind of demonstrated that here today. But more importantly, our relationships affect our ability to design. It's really just more than human interaction. It's just skills that we bring into it. We just have to understand who we're bringing into this and how they work and how they've been trained. Okay? And if we can dispel some of those myths and get beyond these assumptions that we put on engineers or designers in general, then the PCB process will probably move a lot smoother. So who are we? At this point, I've never even introduced ourselves really formally. We are 9.Connects. We're a PCB-centric organization dedicated to training, coaching, consulting, design, and the layout of printed circuit boards. We really believe that the PCB is the medium of all mediums. You can be in the ASIC process, where you make chips. You can be in the system level design where you're making large systems, putting them all together. But at the end of the day, when it comes to really anything that's electronic, you got to have a printed circuit board. And we believe that if you understand where the printed circuit board is, all the other things will fall into place rather nicely. So what do? Well, we do trainings. If you're familiar with us, many of us are experts in Altium Designer. Many of us, including myself, are former employees of Altium. We've come up with our own trainings. So we have our own boot camp, which is an introduction. We also have Spec Ops, which is our advanced training. And we just recently came up with the PCB fundamentals, just understanding the entire process. Go ahead and check out our website. We're finally getting some feedback in from some of our recent classes and you get a better feel for what people feel about it and what they took away from it. If you feel like you understand the PCB fundamental processes, you may still want to take a look at this because you may find a lot of things in there that may have never dawned on you. Because the PCB fundamentals, just the entire process, is simply not taught by academia. They have not gotten past where industry is and where academia are still not congruent with each other. They are still training engineers to be theoretical, and they just don't understand that the industry has changed to the point where engineers really do need to get involved in printed circuit board design. So this is a really great source if you're really looking to get the whole story from specification all the way to fabrication, test, and assembly. We also do something called coaching, and we realize that coaching is just one of those things where it's like, look, we don't want to follow a formal book. We just need help in specific areas, and we can do that. So if there's specific areas of Altium you're interested in, we can train on that, or basically coach on that. If it's process related, like, hey, explain to us more about the manufacturing process or documentation that we need to write. How do we write a spec? We can assist you in the process aspect of it. And of course, if you're one of those companies saying, like, look, for years we've always built this device, it's worked great, but now they want us to hook it to the internet, now they want us to get data out of this thing, now they want it to be wireless, and you're not sure how to do that, come talk to us. We can certainly assist you with that. Okay. Really, for us, we also provide something I'll call consulting, which is kind of like coaching, but it's really going beyond that. It's really partnering with you to understand where you're having some issues. So if you're getting to these technological hurdles where it's like, we just don't know how to do this, or we're going to have to spend a lot of money figuring this out, let us come on in there because we will show you the way. We do believe in giving the fishing pole rather than the fish. And ultimately, we want you to be successful. That's the key thing. So any one of these things, training, consulting, or coaching, we're here to provide that for you. And really, for more information, feel free to check us out at our website at 9.connects.com. So I want to thank you very much for joining us.